All right. So in this session, we'll review and go over how I found multiple vulnerabilities within the Linux kernel and in the Linux kernel drivers in a very easy manner. And hopefully by the end of the session, you will be able to do it as well. So my name is Lossos, and I'm a vulnerability researcher at CyberArk Labs, focusing mainly on operating system internals, mainly Linux kernel, but recently macOS as well. So what we will have on our agenda today. So first of all, we will start by reviewing a little bit of open source research methodologies, followed by how you can integrate the use of static code analysis within it. Afterwards, we'll see how I've used static code analysis in the Linux kernel, with demonstrating and showing some cool bugs. And lastly, we will dive into the so-called main vulnerability, which was found in the NVMe driver in the Linux kernel, with hopefully a working live demo if the demo gods will approve. So, a little bit of open source vulnerability research methodologies. So, the first one is quite obvious. Because we're doing open source research, we have the source code with us immediately. So we don't really need to reverse engineer anything, at least in the beginning. I'll explain a bit more later. But we can just start looking for some bugs. And the cool part about researching open source is that you don't really need to understand, firstly, the code itself. Just by looking at the code, you can find some maybe low-hanging fruit bugs. And another really great thing about open source research is that if you don't understand some kind of the code, a code snippet, for example, you can just search it up in Google or ask your favorite AI chatbot, ChatGPT, for example, maybe it can help you. Static code analysis is a thing. So you can just write your own very custom tools or use existing ones. Just download it from the internet and maybe they can show you some low-hanging fruits. And again, writing static code analysis tool to review open source, it's much easier than writing, scripts with IDA Python, for example. Debugging is a thing. So because you have the source code with you, you can just recompile it, add your favorite printf, for example, if you like to debug like this, and just recompile, and hopefully you can trigger some bugs that you found, potentially bugs. And some disadvantages of open source research, and the elephant in the room here is the bug bounty one. So unlike closed source research, where most of the time you will get some kind of bounty doing it, for example, if you're in the operating system area, so like Windows or some Apple, you will get a bounty for finding and reporting vulnerabilities. And in Linux kernel, most of the time you won't get anything, so it might be less rewarding for bug hunters. And the second one, which is my very own opinion, is that open source might be, again, my own opinion, be a little bit of more overwhelming than closed source research, and I will explain. Let's assume that we found maybe some kind of a bug or some kind of a lead in open source. So I found myself a lot of time just wasting time trying to read code that's not really necessarily in the area of the bug that I found, only because I wanted to understand how the program works, and just wasting a lot of time trying to understand things that aren't relevant for the lead that I found. And because in closed source, you actually need to reverse engineering anything, so you might be more lazy and you don't want to do it. So for me, I wasted a lot of time in open source research, but that's for my own experience. So what will be our strategy in open source research? So first of all, obviously, we need to find the source code, whether it's GitHub, GitLab, whatever, wherever it is, just get it. And then we can just start by looking at the code, static code analysis, looking with our own eyes, using our existing tools or available tools. And after maybe that we found a potential bug, we can just compile it, build and execute it, hopefully trigger the bug. And lastly, we can just repeat the whole phase and maybe consider fuzzing, and more about this very soon. But what about reverse engineering? Do we even need to reverse engineer the open source compiled libraries? So hopefully I will show you a reason why it's still very important to reverse engineer the compiled binaries from open source projects. And let's assume that we have this memcopy function, okay? We might think that it will look very similar in the decompiled code, just preparing some stuff, but basically jumping to the memcopy, right? So I want to show you something. This is a vulnerability I found last year, which is a kernel driver of a very big keyboard vendor, which this function specifically, its functionality is to change the RGB colors of your keyboard, okay? And I'm telling you now that the start column and the stop column are fully user-controlled variables. Okay, and as you can see, I will just tell you, it's a very clear, simple memcopy function, vulnerability, right? Because we have full control over the copy size in the memcopy. Thus, we have a stack overflow in kernel, and it's very easily exploited to local privilege escalation. So if we open it up in like IDA, for example, we might think that the decompiled code will look something like this. As you can see, as you can see, it's very similar to the open source itself. You know, just if we compare it one by one, maybe different, but basically jumped into memcopy, right? But in my case, when I open it, it looked something like this. As you can see, there is a if statement being inserted into the compiled binaries that obviously wasn't in the source code itself. And as you can see, it checks specifically the size being used in the memcopy. Okay, and this is specifically the 45 source mitigation, which basically won't let us to exploit buffer overflows beyond the denial of service maybe. And the only way we could have known that this code was inserted into the compiled binaries, it's either we were genius or we knew all the configuration of the compiler. Or the most easiest way, just open it up in a reverse engineering program. So there's a saying that I really like, which goes like, the code that the programmer writes is only what the programmer intended the machine to do. But if you want to actually know what the machine will run, the only way you can do it is opening up in a reverse engineering program, IDA, whatever you want. So finding this vulnerability took me a little bit of time because I just statically reviewed it with my own eyes. And as you can tell, it's a very simple vulnerability with high impact. And I wanted to see maybe if I could have found it in a quicker way. And for this case, the concept of dumb fuzzing was perfect. Because again, dumb fuzzing is basically sending random bytes into some kind of an interface that we have with our driver here, for example, and just sending random bytes and hopefully triggering some memory or corruption bugs, because it won't really find, most of the time it's find memory corruption bugs and not logical bugs. And if we want to do it in a Linux environment, because here we add it in a kernel module, we need to first understand how we can even communicate with our kernel drivers. And in Linux, there are multiple ways to do it, which we'll go briefly over the main methods to understand them a little bit. So first of all, if we have a kernel module, for example, a lot of time they're just implemented via just exposing a file on the file system, which then can be accessed via just the normal read and write syscalls. It's very common on character devices, for example. And another way to do it is by using the ioctl API interface, which again, it's very common on Windows system. This functionality, unlike they're just using read and write syscall on exposed files, each functionality is most of the time distinguished by a unique command parameter. And then based on this command parameter that we're sending via the ioctl syscall, we can trigger the wanted functionality. My favorite way to implement kernel drivers is by using the pseudo file system, like sysfs, for example, where most of the time each functionality will be exposed on a dedicated file. So let's think that we have this file system, which isn't really files, it's in memory, but each functionality is exposed on a dedicated file. And then interacting with the driver is very easy because, again, just interacting via reading and writing to files in a bash script, for example, is very convenient. But it's not the fastest way, and the fastest way to do it is by using mmap, which is basically mapping shared memory between the kernel space and the user space. It's more difficult to implement, but if you're all after speed, use this. And there's a very nice thing as well that you can do, which I wanted to put here because it's not file-based, is by using the netlink type of socket, which is thus, think it's the same socket APIs, you're just creating it in the kernel side, and you're just using the normal socket APIs to communicate with it from user space. And use it if you don't like files, but whatever. So the dumb fuzzer that I wrote to trigger the vulnerability, as you can see, very simple. Took me less effort to write this than finding it with my own eyes. And as you can see here, my driver was implemented via the sysfs type. Okay? So as you can see, we'll go over it a bit. So as you can see here, firstly, I know the files will contain all the writable files. Okay? The fuzzer function is very simple, basically just sending random bytes. Okay? Nothing special. And the fuzzer is just a while true of picking a random writable file, sending in random data, and hopefully trigger. And it crash the driver. But again, it took me some time to write this maybe 20 lines, 50 lines of code, right? And I wanted maybe to find, is there an easier way that I could have found it? And maybe static code analysis tools could have helped me. But what even is static code analysis? So, static code analysis commonly refers to the running of tools that attempt to highlight possible vulnerabilities, blah, blah, blah. Basically, tools that help me find vulnerabilities, maybe low-hanging fruits or potential bugs. But you don't really need to write your own custom tool. Well, you can do, but there's plenty of it available over the internet. So, for example, if you're reviewing some C code base, you can use Clang's static code analysis or CPP check. And if you're reviewing Python, you can use PyLint, MyPy, JavaScript, ESLint, JSLint. And of course that I had to mention CodeQL here, but CodeQL is a bit more different than static code analysis because it's more focused over the query language itself and not just give me some compiled binary that will statically analyze my source code. Okay, how can we use it against the Linux kernel? Because that's my target now. First of all, which type of bugs I'm looking after if I'm using static code analysis on it? So I'm looking mainly over these 4 type of bugs, which will be just general buffer overflows, underflows, integer overflows, underflows, null pointer references, and uninitial variables. And the static code analysis that I chose for this task, for this project, I had one request. I wanted it to be as simple as possible. And for that, I found this tool, which is called CPP check. And it's very easy to use. You just download it from your favorite package manager if you're going to use whatever you want. And after you download it, you can just do it like this, run the tool against my C source code, and potentially it will help you find some bugs. But if you want a more robust command line, you can do something like this, which basically I'm outputting all the potential error into an XML file. And then if you download it from the source code itself, it has a built-in HTML parser. So you just pass it in the XML and it's outputting HTML files, and then you can just shoot it up in your favorite web browser and it will potentially look something like this. And here you can see you can filter by type of bugs that you want. And here, for example, I chose null pointer, and maybe if you found something, it will look something like this, and maybe something like this. And obviously after this, you have to check for the vulnerability by yourself, okay? So now let's go to the fun part of some bugs. So unfortunately for me, when I checked the CPP check against this code, I hope you remember it, it didn't find the bug. And my assumption is because the static code analysis tool didn't know that the start column and stop column were user control variables. But again, I was thrilled and motivated to see if I actually could still find vulnerabilities with the simplest to use static code analysis tools. And fortunately for me, NVIDIA released their closed source kernel drivers to open source. And you know, if NVIDIA writes some custom tools, there's no chance they're going to do vulnerabilities there, right? And funny enough, there were quite a few. And as you can see, very simple bugs. And then this is the first one. As you can see here, I'm just declaring a null pointer, okay? And let's not look at the config, okay? As you can see, literally one line after where the reference it, null pointer dereference. But still, if we were configured with NVACPI bus get device present, I still need to check the return value of the function ACPI bus get device, blah, blah, blah. And here it didn't check. And if you still don't trust me, this is the definition of the function. And as you can tell, it still possibly can return the device as null. So if we call this, no matter what we did there, it was null pointer dereference. Okay, so I've shown you some vulnerabilities in Linux kernel modules, but what about the kernel itself? So around that time, there was a lot of drama regarding some kind of driver being implemented in the Linux kernel, which implemented the NTFS in the Linux kernel. And for some reason, after being implemented in the kernel, there wasn't a lot of maintenance. And you know, as an offensive perspective, if a driver isn't being implemented, maintained properly, maybe we should check it. And indeed, my colleague and I wanted to check it. And we found this piece of code. I will give you 10 seconds to look, and maybe you can find it while I drink. Okay. As you can tell here, I have 2 pointers, alright? Utter, which is a null pointer, and the second one just a pointer. As you can see, I'm working with the utter B pointer, okay? Utter B is, and I find utter, blah, 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 utter B, everywhere utter B. And here in the end, you see, it uses utter. And it's a null pointer, obviously a bug. And the programmer wanted to work with utter B, but he made a mistake, and indeed, it was exploitable. And if you want to read more about this vulnerability specific and the exploit, feel free to read the blog post that my colleague Alon Zehavi wrote. It's very nice. Okay, now let's go to the juice, the NVMe. So indeed, after finding the NTFS vulnerability in the kernel, I wanted to see if maybe I can find a higher impact vulnerability in the kernel. And lucky for me, Linux kernel version 6, the release candidates of the kernel version were being released now. And I just went over the old patches that there were. And I've encountered this feature, this implementation of NVMe in bad authentication support. I knew what's NVMe basically, something SSDs, right? Maybe my computer has SSD. But I had no clue about what is in-band authentication and support. But again, it's open source. You don't really need to understand, or in the beginning at least, you don't need to understand what the code does. You can just search for bugs immediately. And after shooting up my favorite CPP check, I've encountered this piece of code. And I checked it out, and I reached this code. Can you maybe spot the bug here? All right. As you can see, again, I have no clue what the code does, but all I can see is just I have this CTRL key member under the CTRL struct, and then I'm trying maybe to extract some kind of a key. And if I had an error while extracting the key, I'm just replacing it with a null, and then I'm just dereferencing it in the log. It's in the kernel, yes, it's quite weird. And indeed, if you want now to exploit it, we have to know what's NVMe now, right? Because we want to maybe try to trigger it. So a little bit of NVMe. NVMe is the non-volatile memory express protocol, which is a transfer protocol for accessing non-volatile storage media over PCIe, or basically just the protocol or the specification for accessing your lovely SSD, okay, over PCIe specifically. But if you don't want to transfer over PCIe, it has an extension which is called NVMe OF, which basically lets you to transfer data between connection with aren't specifically PCIe. So for example, over fiber channel or even Ethernet. And NVMe TCP is a specific implementation of the NVMe OF for for TCP specifically. And if we're summing it up, NVMe again is the protocol specification to communicate with your NVMe devices. NVMe OF is the extension of NVMe to communicate over non-PCIe connection, and NVMe TCP is an implementation of NVMe OF for TCP specifically. But where can we even find it? So after looking up in Google, I was quite amazed. And again, Amazon has it for every virtual machine that you have. The default, as far as I know, the default disk for your local servers is based on NVMe. If you don't like Amazon, for example, Azure has it as well. If you don't like cloud providers as a concept, your lovely NetApp on-premise machine has it as well. And if you don't like the concept of storage, your local Linux kernel ships with it. So no matter what is your preference regarding storage, you will have it most likely with you. Okay, so the attack surface might be quite obvious. It has potentially a lot of impact. But how can we even exploit this specific bug? Okay, so we have this primitive of null-pointed reference, right? We have this function called NVMET setup auth, and we have this primitive of null-pointed reference, which will be caused if we have some kind of an invalid key. Again, I don't really know what's a key now, but I know how to make it, because this function tells me what's an invalid key. And I can basically make a key invalid, first of all, if it's not base 64 encoded, or more easier way, if it's not in the length of 36, 52, and 68. Okay, so potentially making a bad invalid key is supposed to be very easy. But fortunately, or unfortunately for some people, there's quite a lot of mitigation regarding the exploitation of null-pointed dereferences in the Linux kernel, which the first one will be the mmap min address, which it won't let you to map low memory addresses. So for example, if you try to map page 0, it won't let you to do it. And if you manage to bypass it, again, you have this smap and smap which you won't be able to access or to execute this type of memory. And if you manage to do both, you have this concept of oops in Linux, which I like to call it maybe a small panic, which basically the server or the kernel reaches some kind of functionality that isn't really good, but it still might be able to run properly after experiencing such a thing. But again, a lot of kernels come with panic on oops, which again, if you reach bad execution or bad code, it will crash immediately, mostly in production servers. And if you want to read more about this, there's a very nice blog post by Project Zero, which still explains again how you can even still exploit null pointed references beyond a denial of service. Really good, right? So go check it out. So how can we exploit our own vulnerability that we just found? So if you remember the patch notes that I've shown you earlier in the long article, I read it a little bit more because I wanted to know more about it, and I saw a lot of NVMe TCP stuff. Okay, and if I know TCP, it's network, right? So maybe we potentially have the remote primitive here. Maybe from potentially a denial of service, we can make it a remote denial of service. And for this, now we need to actually know how the topology looks like. So basically, the NVMe environment looks something like this. We have this host object. In the code, it's called host, but basically it's the client that want to access storage being stored on the target, which is the server that has the disk. Okay, so you have host, client tries to get access to storage from the target. And if we look back at this function, again, because we open source and we want to know how we can trigger this vulnerability, and I'm telling you because I had the source code, this code is in the target, in the server. So we can just go up the call stack because open source, yes, and we finally reach this function, okay? And just by looking with the eyes, this function looks something like a parsing function maybe, because again, getting some kind of rec, I don't know what's rec, but trying to parse something. And if we look who calls this function, we can actually see the NVMe OF implementation. Okay, as you can see, there's the TCP implementation, the RDMA implementation, fiber channel implementation, everything. And because we saw the NVMe TCP, let's check the TCP limitation. And lastly, as you can tell, indeed, there's the generic kernel receive message function being called. So yeah, very likely to be able to remotely trigger the vulnerability. But now, okay, we may be able to trigger it. Let's try to do it, right? So how can I even set up NVMe environment? Okay, now I knew NVMe disks. I know more about TCP, stuff like that. How can I set it up to test it? So by searching up how do you make an NVMe or create an NVMe environment, or specifically even NVMe TCP, it's very easy to do. Okay, just look in Google. It will give you scripts to do it. But again, the bug that I potentially found was in the authentication feature, okay? And as you remember, it was just being inserted into the kernel. So there's no any documentation to it. And the only first way that I saw that how I can trigger it or create my own environment for testing was by reading the source code. And again, remember, I wanted it to be the easiest way I can do. I didn't know, it's hard work for me. I didn't want to do it. But after some more tests, I found this block test framework, which is basically solve my problem. The BLK test framework is basically a framework for testing all the block devices in the kernel. Okay, so for every type of block device that you have, most likely you will have a test in this framework. And indeed, I saw a very newly commit into this framework for testing the authentication feature specifically. Okay, so now I knew how to configure the authentication feature. It was very easy. Just I know how to read. Yes, I can do it myself. Okay, now let's see a live demo. It's not changing screens.
Just to wish.
Yes. Yes. I can just do this, I guess. Okay. Yes. Just restoring snapshots. Is the font big enough? You can see? Oh, okay, perfect. So here on the left, I have the server, okay, of the NVMe server, and I just have a script that will just configure the system for me. Okay, now here on the left, I have now an NVMe TCP server configured. Okay? And now, okay, I'm just showing you the configurations. Oops. Here on the right, I have the so-called attacker machine that I will try to attack the server with. And I didn't tell you, but every host on the NVMe network has a specific unique identification. In NVMe system, it's called the host NQN. And here on the right, you can see that the attacker machine has 84678. And here on the left, I'm allowing this host, the attacker machine, to talk with me. Okay, so I have the 84678. Okay, and now let's try to trigger it. Oops. I'm using the NVMe command line utility, which is just a very lovely command utility to working in NVMe environment. I'm just sending a connection request to the remote server. I'm using it, and remember I'm using the NVMe TCP, so I'm choosing TCP. Connecting to the server. Choosing the port, that's the default port of NVMe. Choosing the subsystem that I want, and hopefully we manage to crash. So that's good. Thank you, thank you. Okay, slides. Should I reconnect it? Yes. Sorry about that.
The signal is already in there, but do you open the mode of like extend or something?
Oh, it's not right.
Extend mode.
Extend, yes. Mirror, you want mirror? Put mirror. Yes. Maybe now again. Here. No, right. This. Okay. It worked earlier. Let's try again. Sorry about that, guys. Technical issues, apparently. Let's try it again before changing. 1 second.
The monitor setting make penalty extend or duplicate.
This is extend or duplicate? Okay.
Try one. Okay.
You have any questions meanwhile, maybe? It is what, sorry?
Default on some...
Good question. He asked if the NVMe comes by default configure, and no, you have to actually configure the NVMe, but it's defaultly shipped with the kernel itself.
Okay. Have you ever find any real target with this port opened?
Found what?
Real target.
This is kind of real, yeah. But yeah, I found them more, but I won't get into them now.
Okay. So is it possible to just replace stably exploit this bug?
Is it possible to what? Exploit it?
Yeah.
It's fixed. I fixed. I sent a...
No. I mean, is it? Can you stably to exploit this bug?
I have another demo that I want to show you, which maybe will answer for you.
Okay.
Is there another hand I saw up? Okay.
Close this.
I have probably a stupid question, but how exactly you're going to achieve remote code execution having null pointer dereference vulnerability?
It's not remote code execution, it's remote denial of service.
So it's low severity vulnerability.
It's what?
Low severity vulnerability.
What? I didn't understand.
I mean, denial
yes.
execution means low severity stuff.
Yeah, it's basically, it's a remote denial of service and it can crush the remote storage.
So there is no code execution, right?
No, it's remote denial of service, I said it. Of course, it's null pointed reference.
Hi, nice talk.
It's not finished yet. Thank you.
We don't know. So I wanted to know, like, since you're using some run-of-the-mill tech that somebody wrote and it's open source.
So can you start from over?
Anyway, so like I know people that for a living at some point in academia they wrote some tools to find bugs in the Linux kernel. There are people fuzzing the Linux kernel like Google and stuff.
I know.
Why is this still like this bug looks like it could have been caught by a linter kind of?
Yes, of course.
Okay.
And that's the funny part. Again, that exactly was my purpose, to see if I can actually find easy vulnerabilities, and again, I will get into it shortly, but low-hanging fruits in major code repositories that the kernel with the most easiest to use. So I was amazed as well that I could do it.
Thank you.
Yeah, of course.
Yeah, hello. Yeah. So I have a question. So when you're specifying the allowed IP addresses that can access...
I did, and I have the second demo that I will show you something else. It will connect to you.
No, yes. The question is like, can you allow any IP address to access?
Yes, you can.
Okay.
You can. Okay, good. Thank you. Okay. So again, after we found the remote denial of service, okay, and as you asked as well, I had to be allowed to talk with the remote server, okay, and the first thing that I wanted to do is to check if maybe I can bypass this authorization request. And the first thing that I obviously did is, trying to connect with an unallowed host. And when I tried to do it, I got this error message. And as you can see, no, I'm not allowed to connect. Okay, and what's the next thing that you might do? Just sniff the request, open it in Wireshark. Sorry, and as you can see, it's being this is the connection request, right? And as you can see, the host NQN is being passed on clear text on the packet itself. Okay, so what are the chances that based on this information, the remote server actually trusts me? Can I maybe change this? It's the common thing to do, right? And now I will show you another demo, which here I won't show it live because I don't want to mess with the virtual machines now. But I will explain. Here on the right, I have the server. On the top left, I have the allowed host, okay, the configure host, or based on what you asked, if it was everyone can do whatever, okay, I quick win. But on the bottom left, I have the attacker machine that I will want to exploit with. Okay, here I have the 3 machines. I have the environment already configured. As you can tell here, again, this is the allowed host. As you can see, it's end with 84 something something, the same as the top left, okay? This is the allowed. And as you remember, the packets, the connection packet is clearly on clear text over the network, over the LAN, yes? Here on the bottom left, I have the attacker machine. As you can see, there's a completely different host and QN. Again, different unique ID. If I will try to connect to this machine remotely, hopefully, yeah, I didn't manage to crash it. Okay, but again, because it's clear text, just a normal network attack like ARP spoofing, whatever, would be enough to get a allowed host and QN, because the host and QN goes plain text on the network. Also, for the sake of the POC, I will just copy it. Okay, I don't want to do network attacks now and stuff like that. It's not very hard. The NVMe command utilities has this flag of changing the host and QN. Very nice. I will now try to change, and yeah, it worked. So now I was able to bypass the authorization feature just by sniffing. I didn't sniff here, but trust me, it's doable. Sniffing and finding the allowed host and QN. Okay. So after finding the vulnerability, I sent a fixing PR to the kernel developers, and they merged it very quickly. A few CVEs, and as you asked, a couple of more under disclosure now. So stay tuned for that. And if you want to read more about the vulnerability, I've just published a blog post about this, which goes much deeply into the vulnerability. I will have the QR later as well, so don't worry. And some key things that I want to mention, which is the important thing, is that, again, as doing vulnerability research, specifically in open source, it might be, again, from my personal experience, a bit overwhelming. So again, focus is the key here. And another great thing is if there's no any documentation, just look for tests. It might help you. And the last thing that I want to say is, as you can see, static code analysis tool is a very, as you saw, I used the most simplest one to use, is a very still powerful tool to use for low-hanging fruits. Again, maybe more robust vulnerabilities, it won't verify very quickly, but again, that wasn't my purpose. And that's basically it. Sorry for the technical issues, but thank you very much. And this is the blog post if you want to read more about it. And thank you very much, guys. Anyone has more questions after the second demo, maybe? Any more questions in general?
Yep, any questions from the floor? We had a few earlier.
Okay, thank you very much, guys.
That wraps it up. Thank you, Tal.
Thank you.
One last round of applause for him. For NVMe, new vulnerabilities made easy.